Hello there, ROS developers, and welcome to a new open class. We've had a break of a couple of weeks without doing the class, but today we are finally back, and we are going to be talking about robot control. So I'm going to keep it very basic. I'm not going to enter into too many mathematical details and so on, also because I'm not an expert on that, but hopefully we can get something and extract a bit of knowledge from today's class. So yeah, welcome everybody, and let's already get started. Let's not lose any more time. Then as always, let me switch here to my computer screen, and I'm going to log in to the construct, and yeah, let me find the open class of today. Yeah, there we go. As always, please let me know if everything is correct. I see some messages here from previous sessions, but let me know if everything is fine. So the image is fine, sound is fine. Can you hear me properly? Yes, no? From what I can see, everything seems to be correct. There shouldn't be any strange issue, but yeah, it would be great to have some feedback so that I can know for certain that everything is working as expected. In any case, as always, the first thing that we need to do in order to start with the open class is to get a copy of today's rosject, right? So in case that there is somebody new that hasn't attended to previous open classes, let me just explain it to you. It's very, very simple. You just have to click on this button that you have right above the chat here, which says fork, and open the class rosject. I'm going to click here myself, and sorry. Then this is going to create a copy of the rosject into your workspace, into your account, and this copy you are going to have it forever. Okay, so if you come back to your account next week, you are going to have this rosject, so you are going to be able to review it afterwards, after this class finishes, of course. Then yeah, so as you can see also, by clicking on the button, this is going to redirect you automatically to the rosject page, which is going to look something like this. Here at the right side, you have the streaming area with the chat where you can type any questions, messages, feedback, whatever you want. Also the live video here so that you can be following. And also it's going to be automatically opened here, as you can see, the notebook of the class. And here in the notebook is where you are going to find all the instructions of the class, the different things that we are going to be covering today. You are going to find them here. Also commands, code that we are going to be using. Everything you are going to find it here. Yeah, so this is the notebook that I'm going to be following as a script, let's say, for today's class. Yeah. Then, all right, yeah, so today we are going to be covering robot control basics. In specific, we are going to be talking about a very specific and very basic controller, which is the proportional controller. Yeah, probably you are familiar with the PIT controller term and so on. So I can see there Thomas Shun. Hello, Thomas. So everything is fine, sound is fine, image is fine. Can you confirm it to me so that I can proceed without worrying about that? Let's see. Okay, I'm going to assume that yes, that everything is fine. Otherwise, probably you would be complaining here in the chat. So yeah, then we can start by launching the simulation. So in order to launch the simulation, the first thing that we are going to do is to open a web shell. Yeah, so let me click here in the web shell button icon, which is the first one that you have here in the bottom bar. So this is going to open a new blank terminal. This is a regular Linux terminal, as you can see. Then here we are going to execute the following two commands. First, we are going to source this simulation workspace right here, and then we are going to execute this ROS launch command that is going to launch a gazebo simulation, a pretty simple gazebo simulation of a two-joint robot. You are going to see in a moment. Here in the gazebo window, there you go. So this is the simulation that we are going to be using today to demonstrate a couple of things. As you can see, it's a very simple two-joint, 2 degree of freedom robot arm kind of simulation. Yeah. Then for now we can minimize this, and we are going to come back to the gazebo simulation later. All right. So yeah. Then let's actually get started. So if everything is fine, let me know in the chat. Have you been able to launch the simulation? Yes, no, any issue there? Have you been able to properly launch the gazebo simulation? All right. So no comments for the moment. Then I'm going to assume that everything is fine. So usually, if there are no complaints, it's usually good news. So it means that you are not experiencing any issues so far, and everything is going according to the plan. All right. So yeah, we have launched the simulation. We are going to leave it here in the background running for now. We are going to come back to the simulation later to test a couple of things in a practical way. And then let's talk a little bit about this proportional control. So actually, in order to fully understand the concept, we will need some previous context. In this case, of course, as always, live classes have limited time. So I'm going to skip all the previous parts and previous explanations. So there are some things that are going to be missing here from the context, but let's try to focus it right now in the proportional control and try to make it as basic and as simple as possible so that anybody can follow. So basically, the general idea of any kind of control system is to establish a desired state in our system. Yeah, this desired state is known as set point. Yeah, and any control system, the purpose of the control system is to, let's say, try to control that our robot, in this case, is as close as possible to this desired value. Yeah, for instance, in a robot arm, in this simulation, we could say that the desired values are angles for each of the joints. Yeah? We want a desired angle for our joint 1, the red one, and another desired angle for joint 2, which is the green one. Yeah? Then our control system should try to make the robot, the arm, in this case, achieve these desired positions. Yeah? Then in a control system, this desired position is known as set point. Yeah? Then what the proportional control system is going to do is to compare this set point, this desired value, with the real value. Yeah? So we are going to compare the desired value with the real value of the system, of the robot. Yeah? And then, depending on the difference between the desired value and the real one, the control system is going to do something to try to stabilize the system. Yeah. Then this difference between the desired value and the real value is known as error. Okay. So here we have a graph that tries to demonstrate this in a very graphical way and very simple way. So let's imagine that our desired value is this green line in the middle, and our real system is this other green curve here, which is kind of a sinusoidal. Yeah. Then if the real system is beneath the desired value, then the control system is going to apply more power. Yeah. And on the other hand, if the real system is higher, yeah, here we are talking about, in this case, angles. Yeah. So if the angle of the system is below the desired one, we are going to apply more power to the system, and if the angle is above the desired value, we are going to apply less power. Yeah, and this is how we are going to try to stabilize the system so that the real value stays as close as possible to the desired value. Yeah, this is the general basic idea of a proportional control system. All right. Then all these can be expressed using the following mathematical equation. Yeah, where Kp is the proportional gain. Yeah, X is the real state, let's say, of the system, and X set point is the desired state of the system. So this basically would be the error, the difference between the desired state and the real state of the system. Yeah. And this U is known colloquially as control law. Yeah. So the control law defines basically the input of this control system. Yeah. Then here we have it expressed without the time variable, and this is the same with taking into account the time variable. Yeah. Then for our specific system, for our specific robot, we are going to say that the desired value is going to be an angle. Yeah? We have the desired value and the real value for joint 1 and for joint 2. And the input is going to be a voltage. Yeah? This is voltage. So in our case, we are going to apply a voltage, which this voltage is going to result in a torque, which is going to result in the joint moving to a certain angle. Yeah. Then for the proportional control equation, applying it to our system, we would get something like this. Yeah. So the voltage that we are going to apply is equivalent to the proportional gain, the Kp, of the multiplied by the error of the system, which is the difference between the desired state, the desired angle in this case, and the actual real angle. Yeah? And of course, we can apply this equation for both joint 1, which is the red one, and joint 2, which is the green one. Okay? All right. Then with this context, having introduced the basics of the proportional control system and the basics of our particular system, let's try to do an exercise, yeah, which is going to put all this into a test. So, given the following initial positions of the 2 degrees of freedom arm robot, which is our robot, yeah, angle 1, angle 2, 10 degrees, 5 degrees, yeah, and the derivatives. So we have to implement a proportional control where the set point values, the desired angle values, are the following. Yeah, for joint 1 it's 50 degrees, and for joint 2 it's 27 degrees. Okay? Then Here we have an image of our robot, and the angles we can see here. So the angle, the desired angle for joint 1 is going to be this one. Yeah, you have it right here, and the desired angle for joint 2 is this one here. Okay? So for instance, for 50 degrees and 27 degrees, we should get something like this second graph here. Okay? Then for this exercise, we're going to use a fixed KP1 of 2, and we are going to play a little bit with the value of KP2. Okay? So for KP1, we are going to keep it fixed as 2, and for KP2, we are going to try different values. For instance, 0.2, 2, and 20. Yeah? And then we are going to see the results of modifying this KP2 value and how it affects our robot, our system. Okay? Then, after our experiments, we have to try to answer the following questions. So, does the proportional control stabilize the link angles to the desired values? First question. Also, no matter whether the system stabilizes or not, which is the best combination for KP1 and KP2, according to our tests? Yeah? And finally, what does happen when KP2 increases? Okay? All right, so let's try to do this experiment. Then for this, we are going to start by creating a Python script and generating some plots using Matplotlib. Okay? So let's go back to our shell here. And we are going to open a new shell, a second shell. You can do this very easily by clicking here on the on the plus icon. Yeah, this is going to open a new blank shell. Then here we are going to go inside this control exercises folder with the cd command, and here we are going to create a Python script, exercise.py. Okay. Now, if you want to visualize all this in a graphical way, you can open here the code editor, which is the second button that you have here in the bottom bar. So I'm going to click here myself in order to open the code editor. Hello, Roberto. Hello there. All right, and now we are going to see here inside the Catkin workspace SRC folder, we have this control exercises folder, and here we have the exercise.py script that we have just created. Yeah, if you open it, you can open it here in the code editor. You are going to see that right now it's empty. Okay, so what we are going to do is to copy the contents that you can find here in the notebook. Copy all these. Yeah, select all the code, copy it, and paste it here to the file in the code editor. Okay, so you are going to have something like this. Now, here you are going to see a bunch of code. I'm not going to go over all of it. Yeah, but basically these are some matrices, some equations that define the dynamic model of our robot. Yeah, of this 2 degrees of freedom robot arm. Okay. All this is explained in the previous steps of this of the course, of the robot control basics course that I'm going to show to you later. Here I don't have time to go over all the details, but basically know that so this is the inertial matrix of the model of our robot. This is the Coriolis term matrix also. This is the gravity vector, and all this defines the dynamic model of our system, okay, of our robot in this case. Then we need all this so that we can predict the behavior of our robot, right? Yeah, and then we are defining other physical stuff like the mass of the links, the length of the links, the distance to the center of mass of the links, also inertias of the links, gravity, value of the gravity, etc., etc., etc. But what we are going to do here is to set and play with the KP values, yeah, with these proportional gain values. Then in our exercise, we said that we were going to use a fixed value of 2 for KP1, and we were going to play a little bit with the value of KP2. Yeah, the first one is 0.2, if I don't remember wrong. Let me go back here to the exercise. Yeah, so we're going to try with 0.2, 2, and 20. All right. Then into this code, we are going to introduce the values of KP1 and KP2. Okay, and also we have to define. Yeah, also we have here several lines of code which are related to my Matplotlib, which are going to help us to generate the graphs, okay, for the system, for the expected behavior of our system. Then the other thing that we have to define in this script is the formulas for the proportional controller, okay? So V1 and V2. Yeah, the formulas that we introduced right here, we are going to put them into our script. Yeah. Then let me get it here from, if you scroll a bit down here to the solution, you are going to find it. I'm going to get it directly from here and copy paste it. There we go. Let me introduce it right here. There we go. Yeah, so the values of the formulas, the equations for V1 and V2, which is voltage of joint 1 is equal to the proportional gain of the difference between the set point angle and the actual angle. Yeah? All right. So now that we have filled the missing parts of this script, we can execute it in order to generate a graph like this one, okay? Then let's start with the KP02. So here, in order to execute it, all you have to do is from the directory where you have the Python script, you can run Python and the name of the script, which is exercise.py, okay? I'm going to run it myself here. And then now, in order to visualize the plot that is generated, you have to go here to the graphical tools. Yeah, it's this monitor-like icon that you have right here, which says graphical tools. Let me click myself here, maximize it a bit. All right. Then, yeah, so here you can maximize it if you want to see it better. Also, you can maximize the display here by double-clicking here in the blue top bar. You'll see in a moment. There you go. Okay, now. All right, so okay, so right now we are getting the following output. This is, yeah, I can minimize this, which actually it's not like 0.2. Let me have a look at the script. Maybe I set a wrong KP value. KP2 0.2. Save this. Okay. Let me rerun it. Okay. There we go. So actually these values are for, I think that these values are not for 0.2, but for 2, right? Yeah, so let me check here. I must have something wrong somewhere here. KP1, KP2. KP2. Oh, this is looking correct, I think. Okay, let me grab the code from here. Ah, no, I think I think this is correct. Yeah. All right, there we go. P1, KP2, and here. Okay, so for 2, for instance, yeah, exercise.py. Okay, so for 2, we get this value, which makes sense. Yeah, okay. Now let me change the KP value to the KP2 value. Actually, I think it's KP2, not KP1, right? Yeah. Okay. So here 0.2. There we go. Yeah, I'm not getting this actualized. I don't know why. Updated. I change this to 20. Yeah, now. Now it is updated, but it's not actually the expected value. Okay, let me do one thing. Okay, yeah, there's definitely something strange going on here. Okay, exercise.py. Okay. Okay. Here 0.2. Yeah, this is what I want. Okay, let's see. Okay. KP. 0.2. Yeah, so this value is correct. 15, yeah, this one is correct. There we go. Okay. And 0.2. Here we have this response. Yeah, so actually there are some plots that are not being generated properly. I don't know exactly why. In any case, the one that matters, yeah, so I was testing this before the class and the plots were being generated properly. Maybe I changed something last time and I didn't notice. Anyways, so in order to not lose a lot of time here, let's keep going, because the one that matters, which is KP2, is working properly, okay? So if we have a look here at the plots, so let me set it to 2, which is the expected value of KP2. There you go. And I'm saying, use Python 3 instead of Python. I don't think it's going to make a difference, sadly, in this case. We can try, but yeah, so this plot is generated properly, which is the one for KP2. What we can see from here is that so here, this is the desired value, right? This straight line that we have here. And the real value of the system is this sinusoidal green line here, okay? So what we can see is that the system kind of oscillates around the desired value. And a very similar behavior goes with the angle of joint 2, yeah? So this one is the desired, the set point, and this is the estimated value for the system, which kind of also oscillates around the set point, okay? Then for a lower value, which would be 0.2, yeah, KP2 0.2, we can see that the behavior is kind of similar, but the oscillations are much more slower, right? So also the estimated values kind of oscillate around the desired set point, but they do it much more slowly. Okay, and for the case of a higher KP, which would be 20, let me change it here, it's quite the opposite, right? So it also oscillates, but it goes much more faster. See? And also here there are much more deviations and so on. So the best, so what we can see is that as KP2 increases, the control system oscillates much more faster. So this is one conclusion that we can take, right? So we can answer already this question. What does happen when KP2 increases? Qualitatively, the link angles oscillate more, but in turn, link angles react faster to the presence of some error. Yeah? So as KP2 increases, we see that the system oscillates much more fast, right? And as KP2 decreases, the system oscillates much more slow. So in this case, the better value for KP2, I would say that it would be something like KP2. Okay? So does the proportional control stabilize the link angles to the desired value? The answer is no. Yeah? So it doesn't completely stabilize, but it tries to, it oscillates around the desired value, right? But we can see clearly that it's not fully stabilized, right? And for the question, no matter whether the system stabilizes or not, which is the best combination for KP and KP2, so in this case, the best one would be 2. Okay? Now, let's try to have a look at this in the gazebo simulation. All right, so we have been checking now here some graphs of how the system would work and generating these plots using Matplotlib. But now let's actually do these tests with the real robot, in this case the gazebo simulation. Okay, so for this we are going to generate a configuration file that is going to allow us to tune these proportional gain values. Okay, so let's open yet another shell here, a third one, by clicking on this Add button. And then here we are going to go to Cacking Workspace. You can copy, as you can see, the commands directly here from the notebook. We are going to create a package named controllers with ROS2 as dependency. Inside here, we are going to generate a config folder. Yeah. If we go now to the code editor, we are going to see we have this controllers package with the config folder, okay, which right now is empty. Then inside this config folder, we are going to create this YALM file. Yeah, a planar 2DOF control unit 2 PID.YALM. So let's create this file inside the config folder. Here I have it, and if you open it right now, you are going to have it, of course, empty. Yeah, because you have just created it. Then in here we are going to paste the following code. Okay, so I'm going to select it here from the notebook and paste it directly here. Then here, what we are doing basically is to define the controllers of our robot, of our 2 degrees of freedom robot, this one here. Then first one, we have the joint state controller to monitor the state of the joints. And here we have the position controllers, which are a custom controllers that we have defined here. I'm not going to go into details neither about this, but if you want to have a look, you can come here to the simulation workspace, SRC folder, and inside here, I think it's course controllers. Yeah, unit 2. You're going to find this package, my controller unit 2, unit 3 PID. And inside here, you have an SRC folder with a C++ file here. If you double click on it, you are going to find the code, the C++ code, which defines the controller that we are going to be using for our robot. Yeah, and you are going to find here all the code, which you are going to see many of the things, well, not many, but some of the things that we have explained in this live class, and many of the things that are explained during the unit, this particular unit of the course. Yeah, so what we are doing here is a very small section of a unit, of a chapter of the robot control course that we have just published. Yeah. And you are going to find here many things, many formulas that we have defined in this unit. All right. So Yeah, so let me close this. Then in the configuration file, where we are specifying this custom controller, we can specify the proportional gains right here. We have the gains for join 1, the gains for join 2, and the desired set points. The set points, we already have them here, to -50 and -27 degrees, which are the set points. And as for the proportional gains, the KP value here, we can set them here in the first value. The first value is for the proportional gain. Yeah, second one is the integrate controller, and this is the derivative controller, which are other controllers that we are not going to cover in the live class, but they are covered in the course. Okay, so what should I put here? Can somebody tell me in the chat what value should I put here in the first value of the gains? Taking into account the experiments that we have just done and the plots that we have visualized for the different KP values. Well, actually the solution, you have it already here in the notebook as well. Okay, Anna says 2 and 2 for KP1 and KP2. Very well, very well. So here you have the solution. Then for KP1, which is this one, I'm going to put 2. And for KP2, I'm going to put also 2. Right? So I can save this now. And in order to launch the controller, all I have to do is to run this command. However, I'm going to restart the simulation to make sure that everything starts clean. Let me just restart it by Control-C here in the simulation terminal. And let me relaunch it. And then here I'm going to run the command to start the control system, which is this one. ROS launch, planar 2DF, unit 2, planar 2DF, control.launch. Okay? Then what I'm going to see is how my system starts oscillating. I should see this behavior of the system. We can see joint 1, remember, is the red one, joint 2 is the green one. So the system at this point is going to go back. You will see, there you go, and it keeps this oscillation that we were visualizing here in the graphs, right? For the case of KP2 is this one. Yeah, what we are seeing here is this oscillation, yeah, that we predicted here with the plots, and we can see here in the real robot system now. Okay? All right. Then we can have also a quick look here, if you want, to this launch file that we are running here, and you are going to see that it's in planar 2D of control launch, planar 2D of control. Yeah, this is the launch file that we are running. And you can see basically that what you are doing here is to load the YAML configuration file. No, actually it's not this one. Oh yeah, it's planar 2D of unit 2, planar 2D of control. Ah yeah, it's not this one. It's this one here. Planar 2D of unit 2. Launch, planar 2D of control. Yeah, this one it is. Okay? Here you can see that from the controllers package that we have created right now in our CAD-King workspace, we are loading the YAML file, this YAML file that we have just generated, and configured it with the set points and KP values. Okay, and then we are loading here the joint state controller and the joint position controller, which are defined both here. Okay. So yeah, as you can see, the system is not stabilized. So what could we do at this point in order to improve the system? Well, we could use a derivative control, yeah, or even after the derivative control system, we could use an integrate control system, yeah. However, we are not going to cover this because it would be too much. So for this live class, I'm going to leave it here. I think that the basic point that I wanted to explain in this class has been made, which was introduce this proportional control, which is a very simple and basic control system, and to demonstrate it, seeing some graphs, but also applying it into the simulation, okay? Then this is just a very, very small part of the robot control basics course that we have just published it into the Academy. I left you links here in case that you want to check it. In case that you are interested in learning more about robot control, you can find the course here in our Academy. All right, and the live class that we have just done today, it's a very, very small section of this unit, of the PID control unit. Okay, it's just a very small section of this unit, because we have only covered the proportional controller, yeah. And yeah, I think I'm going to leave it here. So yeah, thanks to all of you for attending this class. I hope that you liked it. I hope that you have learned something. You can remember that this project is for you already, and it's going to be for you forever. So you can keep practicing if you want now after the class finishes, or even during the following weeks or months. You are going to have access to this project in case that you want to use it. And yeah, thanks a lot. Remember also that yeah, so we are going to come back next Tuesday with the next open class. I will see you then. And yeah, so that's all from my part. I hope that you enjoyed it. As always, take care and keep pushing your ROS learning. Bye bye.